Good morning, everyone. I hope you're enjoying this lovely sunny Seattle morning. My name is Sean Dara. I am with the Lighting Design Lab. Thank you for joining the third of our series on heat pumps and how we can use them for energy effectiveness throughout our area. A couple of little housekeeping announcements first. We here at the Lighting Design Lab are delighted to be powered by and a service of Seattle City Light. So thank you to Seattle City Light for providing us for these things. A couple of housekeeping announcements. You will be muted throughout the presentation. However, if you have questions, please type them into the chat area or questions section, and I will be curating them throughout. I will look for those and we will try to answer as many as we can, as expeditiously as we can throughout the talk this morning. A recording will be available for this seminar, as well as the handouts, and you'll be able to find those at the Lighting Design Lab webpage under the Education tab, lightingdesignlab.com. So this morning we are fortunate to have Duane Jonlin from SDCI, Chris Little from Rushing, Julie Banerjee and Emma Johnson from Seattle City Light CCES, and Sarah Braun and Colleen Butterfield from Energy Solutions, sharing their knowledge and information with all of us today. So with all of that said, I believe that I have gone through all of the housekeeping that I needed to go through. So why don't we hear a brief word from Emma Johnson before we jump into Duane and Chris's presentation. Thank you much. Emma, take it away.
Good morning, everyone. So this presentation is going to give you a flavor of commercial heat pump water heating, and we wanted to provide a little bit of context for the issue. Historically, we've seen that the market for commercial water heating is fairly slow to move. Over a 5-year period, 73% of commercial water heating was gas, and only 5% was heat pump water heating. So we really want to shift that percentage and looking to code and other tactics such as training to help move the market. We also found that similar percentage on residential, only 7.7% was heat pump water heaters. And most of those were going into new construction. Interestingly, NIA found that most of the multifamily units were low-rise multifamily, and that's a regional perspective, not just Seattle, and they were in-unit electric. So there's really a good potential to shift that market towards heat pump water heating. And also in downtown, we're seeing a really strong residential market happening, and they're either completely residential condos or apartments or mixed use, with 66% of new projects have a residential component, and over 38,000 are residential units or hotel rooms. So we're seeing that really being a dominant perspective. So Duane and Chris will talk about how we can move the market.
Is that it, Emma?
That's it. Go for it.
Okay, we'll be talking to you all at the end. So who's this guy with us? Chris, you want to introduce yourself?
Yeah, hey everybody, I'm Chris Little, manager of engineering at Rushing. I realized I probably should have put a Rushing logo on the slide, Duane, so I might follow up with that. But I've been doing plumbing for the better part of 14 years. First 10 years was actually in Atlanta, which I think of as the land of the gas boiler. Doing things like labs, institutional work, a fair bit of multifamily. Atlanta had a lot of renovation and repurposing projects I worked on. So moved up to Seattle about 4 years ago and have been working at Rushing. And then been exposed to heat pumps for the first time in Seattle. So thrilled to be exposed to it. A little bit about me, not work related, is I'm an avid DIYer, right? I like to do stuff that I've never done before. And then all of a sudden you know how to do it. So kind of my spirit there. I'm also a chicken farmer. So if anybody needs any eggs, let me know. They're organic, $4 a dozen. But yeah, that's it. How about you, Duane?
Well, I think people are getting tired of seeing me coming up on these slides, but yeah, I've been working in Seattle for a long time, and for the past decade, instead of architecting, I've been working on the Seattle Energy Code full-time and more than full-time. And actually that fourth bullet over on the left there just came in a couple of days ago, that I was just nominated to be chair of the IECC nationally. So we will see, we'll see what Seattle influence can have on the rest of it. But that little phrase on the right, I just wanted to say that the whole point of this presentation ought to be, we got it, we can do this, it's not going to be that bad. And what's special about Seattle and Washington State is that we have on the books in legislation that we're going to these high levels of efficiency. The question is not whether to do it or not, like it is in most states, it's what's the smartest way to get there. So today, obviously, we're on to heat pump water heating. And of those 4 guiding principles that you might have seen if you've seen my earlier talks, it really focuses on those 2. We can't be carbon neutral a few decades from now if we're installing new gas infrastructure through this decade. We also can't just be wasteful with electricity and start using electric resistance. So that bottom line is the bottom line. New buildings have to be capable of getting there to that carbon neutral target without major surgery to the building in the next couple decades. So this is the core of the code requirement, and we delayed this several months so that it would give design and construction and manufacturing people time to get ready for it. But projects that apply for permits after January 1st of 22, their hotel and multifamily have to do their water heating by heat pump. There is in process now, slowly, a proposal that came from City Council to extend that requirement to all commercial buildings that use substantial amounts of hot water. And we're just saying no more gas, no more electric resistance. We're going with heat pump. And we'll have lots more detail about that. But if you want to do something fancy, if you want to do ground source or a big solar thermal array or something, hey, we will not stand in your way. Now, this is the first of Chris's slides, and it's just kind of a review, kind of a preview of coming attractions that are coming up on the next number of slides. And there's also a little warning down there in the right-hand corner at the bottom. Chris, you want to give a little intro to this slide?
Yeah, there's a couple warnings. This is a dangerous slide, so don't take this slide fully at face value, particularly the capacity columns, the COP columns, and the amps voltage columns. Capacity for heat pumps is wildly variable, right? It depends on outdoor air conditions, incoming water temperature. So those numbers that are shown there, you need to get more intimate with the cut sheet and the data sheets from the manufacturers before you just run with it, right? And COP stands for coefficient of performance, which is basically the heat output by the device divided by the heat input of the device. Again, changes wildly depending on the conditions that the heat pump is operating in. So, and then voltage. So a lot of manufacturers list full load amps on their cut sheets, on their data sheets, which is good. That's good data to know. But these machines have a lot of mass in them and a lot of inertia. So like inrush current, startup current, to turn them on, a lot of times you'll see a current jump for a while and then it flatlines it into like a steady state. So that clip at the bottom, you can see, I believe this was taken from Link. The largest unit full load amps is 83 amps, but just to get it moving is 268. So make sure your electrician's aware of all that data so that you don't start tripping breakers. Word of caution.
And that's kind of scary. That's that startup current is 4 times the full load current. So it's pretty
Correct.
serious.
Yeah, that's to kick on compressors, get fans spinning, get refrigerant flowing. It's it's impulse at the beginning, but it's something you can't ignore.
All right, now we're getting into the lovely diagrams here. So this is my concept drawing of a basic heat pump water heater system. On the left, there's that heat pump. It's pulling heat out of the air, and that water's coming into the main tank 40 degrees and going out the top at 140 or something like that. It's pretty impressive technology. And if you're in a building with a big recirc system, then there might be a heater and a recirc tank just devoted to the restoring the heat losses that happen as that water is traveling around the building. And you're going to chime in on some of these, aren't you, Chris?
There are some later. I was planning to chime in on the next one, but yeah, I mean, this is the general scheme. You can change components, and you'll see that as we go here and there based on single pass or multi-pass for your recirc. But in general, this is the overall concept. Heat pump over to the side, generating hot water as the primary, and then you're pulling water back from your loops and reheating it somehow, basically.
And those tanks remain full all the time. It's just the amount of full that is properly heated that varies. Is that right? That's
correct. Yep. You're always going to want to pass through a mixing valve for your final temperature delivery to keep from scalding folks.
So I've been trying to wrap my head around what is a heat pump. That oval in this diagram is this fluid that kind of keeps rotating around and around and around, and it's taking advantage of the phase change, how much heat can be absorbed or released from that fluid as it goes through its phase change from gas to liquid. So, like it shows on the left, you got winter air coming in. You got, it's 40 degrees out or something like that, and going through this evaporator is just absorbing heat into the refrigerant, and that air that's coming out the top is way colder. And then you compress that. That's where all the energy is used, and it gets really hot. And then that hot fluid can get transferred into the cold water that's coming in, and then we just cycle through again and again. That it's kind of a miracle, but if you're comparing this to an electric resistance heater, that compressor is using about a third, or in warmer weather, less than a quarter of the energy that the electric resistance would be.
Yeah, and one thing to add here is that that refrigerant inside the refrigerant cycle, like that refrigerant can change, and that cause the equipment to behave differently. Different manufacturers pick a refrigerant to kind of specialize in for that device, and then sort of exploit its parameters. And so that's just one thing to know. There's a lot of different refrigerants offered.
So another thing from the code here is that there's a couple flavors of heat pump water heaters. One is a single pass, and one's multi-pass. We're going to get into that in a second, but for the single pass water heaters, like I showed you in that first diagram, the temperature maintenance heating for that circulating system, especially in the slow hours when there's not much hot water being used, that has to be separate, physically separate from the primary service water heater, because that is optimized to boost water heat temperature a lot. A multi-pass heat pump water heater, by contrast, is just boosting it 10 or 15 degrees each pass through the water heater, and that could do fine reheating that recirc water.
Yep.
So
single pass tends to be a little bit more efficient, by the way. than multi-pass. That's just one thing to note, because the stratification, you see it on this diagram, the stratification in those tanks, you want your cold water at the bottom, which goes into the heat pump for a single pass device, gets that big high delta T to deliver 140 and sticks it in the top of the tank. If you jumble up those levels of temperature gradient, it compromises the COP, and that's what multi-pass units do. They kind of de-stratify a little bit. Did you have more to add here, going out, or you want me to keep going?
And I've heard from some engineers that if you're doing the multi-pass, it is sometimes hard to control that intermediate temperature, and easy to confuse the thermostats. One option is what's called a swing tank, and once again, I've heard of control issues with this, but this just has an electric element that's in that tank that's receiving the recirculation water, and it's gonna just add heat back in that was lost out in that pipe loop.
Yep. Could you bounce back one slide as well? I want to mention something, Duane. So on the left, the single pass diagram, you can see that circ heater and the circ tank shown as a separate decoupled entity. You can have just an electric tank type water heater serve that same purpose with a resistance element inside of it, or you can have an electric instantaneous device outside of it. But you can also have a heat pump serving your recirc, right? And on our LBPP projects, for those of you who aren't familiar with it, it's Living Building Pilot Program. That's an incentive program that helps with some building feasibility. But there's a pedal that you can pursue called the energy pedal that's EUI based, so energy use index. So the amount of energy that you use is sort of what you're graded on to achieve that credit. Those LBPP projects that pursue that often are forced into heat pumps for that recirc heater, meaning electric resistance, it doesn't pencil, right? It's too much energy loss. And so while those recirc heaters are usually small in capacity when they're heat pumps, they run for the entire year, really the entire life of the building. And so that energy delta is just massive when you figure it up. So one thing to keep in mind, heat pumps can be used as recirc heaters.
So that was the swing tank. For system sizing, you see on the top there, it says 100% at 40 degrees and 50% at 24. 24 is our design winter temperature here. So the primary thing the heat pump has to be sized so that when it's 40 degrees out, it can provide the hot water you need as calculated, and also the heat pump has to get at least 50% of that water capacity when it's freezing cold out, when it's 24 degrees. And then there's an exception below that says, okay, if you got your heat pump in a below grade garage, don't worry about it because it stays relatively toasty warm there. But it is that's the criterion by which you're sizing this. So we'll get into this, but you can have some supplementary heat for very cold weather.
And one thing to mention is just with this, nailing down your demand and right sizing your system, you just got to get really familiar with how your building's going to behave. Like, is it a market rate apartment? Is it student housing? 30 gallons per person per day is, I would say, on the conservative side of that, initial demand target. I think market rate, we're seeing more like 25 gallons per person per day as a normal, as a general rule of thumb. Student housing, for example, is a lot less water. It's like 1 to 15 or 16 gallons per person per day. And I think that, for one, maybe students don't take as many baths as they ought to, or perhaps some off-site laundry that extracts some of that hot water consumption out of the building envelope. But so when you nail down this number accurately, that's your starting point. You have to figure out what your demand is, and then you can get into equipment selection. But that's rule number one.
All right. So that is becomes this design question. Is do you have a whole lot of heat pump capacity so that you could replace all that hot water from the morning rush in very short order, just using your heat pumps? Or do you want to like skimp on the heat pump capacity and put more storage capacity in, so that when you're up against your next morning rush, you have enough, to carry you through that whole storage? And that is an economic and technical balance. I think Chris had a thing or two to say about that, right?
Yeah, I mean, the heat pumps are expensive, right? If you haven't priced one yet, when you do, you'll realize that. There's a fine balance, right? You can't rely on too much storage, and you'll see it here in a second. But you want to avoid getting into a scenario where you're banking on too much storage and not enough heat pump, because the heat pumps are not able to re-inventory those tanks for your dump load. You also have to be aware that some manufacturers limit their runtime per day. Thinking that you can run them for 24 hours isn't necessarily always the case. Comac, for instance, likes to have a maximum runtime of about 16 hours. So that's only 2/3 of the day that you can bank on the heat pumps functioning. I also got to be mindful of defrost. Once you hit a temperature of about 35 degrees, you'll start getting frost on the coils, and they have to, temporarily pause their operation, melt the ice, and kick back on. So there's a little bit of, got to be careful getting rid of too much heat pump. Otherwise, you'll get phone calls from your tenants.
Right. So there's this nifty tool that Ecotope developed, I think originally for state of California, and that has allows you to play with that balance between storage and heat pump capacity. And this is actually a screenshot right out of one that I'd used, where I just sort of randomly put in a bunch of specifications about the building that I was doing, and it generates this. So let's see if this magic will work here. Hey, look at that. So there is there's that diagram. Hello, where are we? Should have we had it up here just a second ago. Sizer system. So with this, given that I've just inputted, a different building, 300 units and a certain amount of usage per day, like Chris was just saying, he thought 30 was a little conservative. So here's 25. That's how much water then you're going to need, and you'll lose a certain amount in your apartment. You can play with any of those to see how it works, but you can see with this slider here, with the tank volume being on the bottom and the of that chart, and the heating capacity of the system on the left side, you can sort of move yourself along that line that it's going to set up. So you could have a very, like I have right now, a very large amount of heat pump capacity and really small amount of storage. Or you could go to the other end and have much smaller heat pump capacity, much larger storage, and since obviously heat pumps don't come in just continuous increments, you could maybe say, okay, I only want 4 of this particular kind of heat pump, and that would be 3,000. I mean, that would be about 700 kVTUH, that would say, okay, now you have to have 3,000 gallons of storage in your primary tank. You had some advice about this, Chris.
Yeah, well, one obvious thing is that note that y-axis doesn't go to 0, right? There's a threshold. Looks like maybe about 5,500 or so gallons. That amount of heat pump. If you slide all the way to the right real quick and see what that maxes out to be. The little blue grabber at the bottom. See that thing? There you go. Yeah, so that's telling you with 419 MBH worth of heat pump, you don't want to go more than 5,400 gallons. If you do, it's potentially not going to re-inventory. So just hammering that point home. Make sure you honor that balance. So scroll down just a little bit. There were some more inputs here. This one's not getting into the load shift, but on your screenshot on the slide it did. So load shift is basically it's think of it like a heat pump blackout, and it's like a mandate or some sort of incentive from the utility company to say, okay, I know you want to run your heat pumps at 7 a.m. to 10 a.m. because that's when you just use your hot water, but my grid's really churny right then. Don't run them then, let's run them later to try to get your, and the SCL folks, you can probably help me with this because I'm a plumber trying to talk electrons, but basically you shift your load out to minimize the impact on the grid. What that does to the equipment is that makes the equipment have to stall and basically be oversized to account for any usage that happens when that heat pump wants to be running. So just keep in mind that if your project is under some sort of load shift requirement or elective, you're most likely going to need more storage to get you through those blackout periods. So, and another thing this does is it calculates heat loss for you. It could either be entered in a watts per unit type input, or it can be just a traditional GPM and delta T, but it'll spit out a capacity for whether you're doing a swing tank with a resistance element or a sidecar heat pump, it spits out that capacity such that you can design that as well. So pretty nifty tool EcoTope has come up with.
Yeah, and you can see here this is from 4 o'clock till 9 o'clock. It's saying, okay, you're shifting off of those hours in particular, right?
Yep, exactly.
So, lots of stuff to play with there to optimize your system, and there was you mentioned, Chris, that the heat pumps are more expensive than the storage.
Oh yes.
The storage though takes up a lot of space, right?
Absolutely. Yeah, I mean heat pumps take up more space also, but they can get more dense, right? They just get a bigger, heavier box. But yeah, storage is going to definitely take up more real estate, also more weight, right? Structurally speaking, depending on where you got it in the building, that's something to think about. And we'll get into that here in a second as well.
So that would be once again on the slide. There's the website. It's a free tool. You can pull it out, and literally with each of these examples I looked at, being in kind of a hurry, I was able to input all the information and start playing with it in 5 minutes or less. So it's pretty convenient, and it's a good way to, especially if you've got to estimate things at early design. So there's a project that is based on fact, based on a real world project that Chris can tell you about how much space that takes.
Yeah, it was just an apartment project in Seattle, 228 units, market rate apartments. But we did 2 different scenarios for the same project, both a RCC in the garage and then a rooftop, which we'll get to in the next slide. But so first, the garage layout. These systems are pretty cool in that they work in tandem with your garage exhaust system. So they pull air out of your garage, which tends to be about 40 degrees in Seattle if it's subterranean and not super open sides or whatever. and then they'll discharge it to the garage exhaust shaft that you see there. But one thing to keep in mind is what's not shown in this diagram is over top of those blue boxes, those RCCs, there's a big sheet metal plenum, right, to convey that air directly to that shaft. So what you need to keep in mind is head height in that room, optimizing the layout of the equipment to make that head height work. That sheet metal plenum, I mean, this system right here is 40,000 CFM worth of flow. So I forget the size of the duct, but it was significant. You can squish it and pancake it a little bit, but it's got to get that air over to the garage exhaust shaft.
Gentlemen, apologies for the interruption. Duane, can you go ahead and go full screen into presenter mode, please?
Oh, sorry about that. There we go.
Thank you.
There we go.
Chris, how tall is each of those RCCs?
I want to say these, with their isolation and their housekeeping pads, coming in a little over 7 feet. So this being at a level of the garage that has some extra head height to get to digest that plenum that I was talking about. There are other options to kind of put the plenum behind the unit if you pull it away from the wall, but you just got to get to know your data sheets, get friendly with your manufacturer's reps, and get educated. But it's a sort of a paper doll thing at first, and then all the information starts to come together to see if it's actually constructible. But one thing I want to mention is that mid-rises tend to be a little bit more friendly for garage-based heat pump plants because of the size of the garage. For one, it's going to cost some parking. I think this one costs about 6 stalls worth. You can also find little pockets of like mechanical mezzanine potentially in some projects to suspend them up above parking so that you don't lose parking spaces. But with that big garage floor plate, you're naturally going to have a big thirsty garage exhaust system that wants a lot of airflow. So like I mentioned, this is 40,000 CFM, works really nicely with that size of a project. When you start talking about the high-rise projects would have usually postage stamp, relatively speaking, floor plates, the CFM requirements are a good bit smaller for the garage exhaust. So sticking one of these in there would be potentially having larger than necessary garage exhaust shafts or larger than necessary louvers, discharge louvers at the alley. And those are always complicated to coordinate mechanically, as most of you know, I'm sure. Another thing before we leave this slide is high rises, you have to think about water pressure for a second. You've got to pump all of your both domestic and hot and cold water up to the top of your tower to have adequate pressure to flow your fixtures. Well, at the bottom of the tower, that's usually 200-300 PSI. You can't put that water pressure through these units or through the thermostatic mixing belts. They usually, start breaking about 125 PSI or 150 PSI. So what you have to do, if you do find a place to get it into a high rise, you have to have a downstream domestic hot water booster to lift that pressure after it's heated. So don't boost it before it goes in, but boost it after it goes in. It's just strictly a domestic hot water booster.
Okay. This could take six parking stalls, but actually in most garages, you'd be turning a corner down there, and those last two, are essentially just dead space there. So probably for this, you've really lost 4 spaces.
That's right. Yeah, those corners, they usually turn into storage rooms or something like that, bike storage maybe. They're good real estate. In fact, you don't have to put your RCC plant on one level. Say you wanted to confiscate those dead corners on multiple levels, that's fair game. You just pipe up and down through the levels, and you're good to go. So
the reason we're in a garage with this, I mean, besides the fact that space is cheaper, is that it's pretty remarkable. They just don't get cold, like they don't ever get hot. I did actually monitor one garage. We had a cold snap a few years ago where it was in the low 20s for a few days in a row, and the spot I picked, which was only like 80 feet away from this big 30-foot wide entrance, never got below 50. So you're pretty safe. There's just the mass of the the garage itself and all the dirt that it's connected to just keeps it at this stable temperature like your wine cellar.
Yep.
Okay, now here's the same building, but looking at what would happen if you put all that on the roof.
Yeah, that's right. And it didn't cost you any parking stalls, so win there. But what it does create its own separate set of challenges. As you all know, in Seattle, you got other trades to think about. On the roof, you got PV requirements that you are going to battle for your land, for your real estate. Green roof, rooftop amenities. So maybe not necessarily easy peasy just to put it up on the roof. It's always a push and pull. You don't have a sheet metal ductwork thing anymore. These heat pumps tend to not be non-ducted and kind of blow right into the atmosphere. But going back to what I mentioned previous and what Duane mentioned is those tanks. Those tanks are, substantial amount of water in them. This plant, we pulled all the cut sheets together and added water weight and everything. This is 60,000 pounds of weight on the roof. So maybe not as big of a deal on a high rise, but on a mid-rise wood frame project, it's something to definitely make sure, you're thinking about, you need to know structural weight, high rise, mid-rise, concrete, wood, regardless, right? But it's particularly sensitive when it's a stick-built building. Another thing that plumbers have not really been sort of hampered by before is acoustics, right? Back in the day before heat pumps, an acoustician asked me for my equipment. I send circ pumps, booster pumps, and don't ever hear back because they're uninteresting, right? Now, when I send my equipment packages over, all of a sudden they start caring about where these things are placed or how they're supported from roof structure in terms of vibration. Another thing is adjacency noise, like adjacency to neighboring properties, adjacency to balconies and outdoor amenities. So it makes the plumbing designer's world more complex as compared to how mechanical is, right? When they put the rooftops up there, you have to get in more of a dialogue with the acoustician about how they sound. So,
and each of those tanks is more than 2 tons, and I think the heat pump water heaters are about a couple tons each. Is that right? So
yeah.
So your structural is going to give you one of those looks. You could imagine though, if you lined those up so that they were over a column line, it would help. But that's going to be a bunch more seismic force for them to deal with since it's high on the building. And now, question for you, Chris, about noise, because those little stand-in units that I've seen, obviously these are the big Mitsubishis, right? But they're
right. Yep.
They didn't. So with other CO2 heat pump technology, is it also tend to be really quiet?
Yeah, they are quieter, and it all kind of depends, right? What I think to be loud is not necessarily what an acoustician thinks to be loud. I don't know the data off the top of my head about a stand-in, but they are listed as particularly quiet as a benefit. But they're smaller units, right? So when you put 20 or 30 of them together, how does that compound acoustically? I'm not 100% sure. My guess is probably not much, but yeah, that's a fair point. Absolutely.
And that one comment about interaction with PV is if you've got that enclosure on the roof for that equipment, then nothing going to stop you from lining the roof with some of your PV up there.
Absolutely, yeah. And there was even a project that we looked at 6 months ago that actually, the whole roof needed to be PV. It was the LDPP project trying to chase the energy use index. And we had PV panels over the entire roofscape, mechanical portion of the roofscape, and there was enough gaps in the PV panels to allow breathability of the heat pump. So it's not, you can be creative. They were suspended, I think, 4 or 5 feet above the heat pumps. So it wasn't a deal breaker. We found a way to satisfy everybody. So.
Right, make good use of that roof. Okay, now I'm gonna turn Chris loose to several slides worth of real world equipment, just because we thought it would be good for everybody to know, since we can't be out on a site together stomping around and looking at these things in real life. Take it away, Chris.
All right, so we'll start out with the CO2 devices. This is Sandon. So these are pretty small units, right? They've got, you know, about size of a suitcase, we'll say. They can operate down to like negative 24 degrees Celsius. So they've got a lot of robustness there, and they maintain their capacity and COP pretty well. One thing to note is that they have a limitation of piping distance from the heat pump to the tank of about 66 feet. So you can't shove the tanks, you know, at the remote other end of the project. Okay. Let's go ahead and go to the next slide, please. All right, so you can see they can also be suspended. One thing to keep in mind is having them accessible for maintenance and things like that. This one looks like, on the left, looks like a person lift would be required. So, sorry, getting a little bit of jitters for some reason. So, but they're not ductable. These units they're blowing right into the atmosphere that they're in. One thing you want to be careful about is packing a corner of a garage super tight with these units, right? They can super chill that corner, and that's going to compromise the COP and the functionality of those units. So you want to kind of breathe them out, get them spaced out appropriately. The picture to the right is actually a pretty nifty idea. Putting them in a kitchen, right? Kitchen is going to be chock full of heat, right? Regularly with gas cooking and commercial cooking. So something to think about if we ever get to, like Duane mentioned, a commercial requirement for heat pumps. A commercial kitchen is a pretty decent location for a Sandon.
And you might want to think about that just strategically in general. Is there some place that you have consistent heat dumping into a space that you then have to pay to get rid of? Maybe if you also have consistent need for hot water, you could be dumping that heat from whatever process load you got right on into your water heating and save on both ends.
That's right. That's right. So let's go to the next one real quick. So this is a new unit by Mitsubishi. It's called the QAHV. That's going back to the diagram that we showed a minute ago. So they're first of all, they're available in August of this year. But these things are much larger than Sandons. They have 136 MBH worth of capacity as compared to that 15 that I mentioned. They maintain that 100% capacity down to about 36 degrees, but still will continue functioning down to negative 13. This going back to CO2 as a refrigerant, it's a lot more robust and can handle those lower outdoor air temps. One thing to mention is that, you know, they only offer one, unit, one model number at the QAHV, but it has 3 different modes of operation: a 40 kW, 50 kW, and 60 kW. And what that does is the 40 kW setting is it sort of maxes or limits the capacity, flatlines the capacity with still the same infrastructure in the unit. And that prioritizes the COP. So, but you have that 60 kW input that you could switch to, say it was a colder time of year or something where you really need to push the envelope and get more heat into your water. That's an option as well. It's just going to dip your COP down. Excuse me. Thing about these units though is they require a double wall heat exchanger that Mitsubishi provides, but those are not inside of that device. So that double wall heat exchanger protects the equipment from, protects the potable water stream from contamination. So it's required, for people to be able to drink the water basically. But those devices need to go in the room, the heated space with the tank. So separate, you can run the piping length that I mentioned from Sandon of 66 feet. This device can pump up to 196 feet horizontally to those heat exchangers. So there's a lot more variability, and you can see them tightly compressed, located together on the roof. So it's pretty tight little package.
How tall is that unit that we're looking at?
I believe that's 6 feet. I have to double check and pull up in cut sheets, or anybody here when they look at a QAHV, look at your cut sheet as a reminder. But yeah, it's not too terribly tall. It will be on some sort of go back to acoustics, some sort of isolator, right? It'll be raised on a spring or something like that, sleepers. So add probably, I don't know, 18 inches to whatever that device is for safety's sake.
So we're looking at needing 8 feet or something like that. I'm thinking if it's a rooftop thing, then what?
You're talking about screening?
Yeah.
Yeah, they'll want to go behind a screen wall for unsightliness, but also noise, right, for adjacent properties, and probably a rooftop amenity close by. There always is. So, well, you can array up to 16 of these devices together, which is 3,200 MBH, by the way. That's massive. So, okay. All right, so then CO2 is getting even bigger. This is a new product from Link, who I believe is associated with Watts as a manufacturer. So this is the Aegis A. They also make an Aegis W, which is a water-to-water heat pump. We're going to focus on the Aegis A today. It's configured in single pass, and it's got 3 different sizes ranging from 191 to 430 MBH at 45 degree outdoor air temperature. So the size of this unit, Duane, is about 12 by 5 by 7, 7 feet tall. But that capacity, it's a 430 MBH, that capacity is equivalent to 28 Sandons inside that box. So when you think about it, you know, the space that Sandon takes up is sort of peppering a floor plan or a roof plan. This can be sucked into a tiny box and generate equivalent of 28 of those things. It's just insane to me. They're only offered at 480 3-phase though, so that's something to be careful about for a mid-rise project. Most commonly, they do not have 460 available. It's 208 generally. So if you wanted to use it on a mid-rise, you got to have a step-up transformer, which is not the end of the world, but just know that. They do have their own line of tanks, 250 to 1,000 gallons worth of. But and I'm not 100% sure if you have to use their tanks. Some manufacturers are kind of persnickety about letting you use aftermarket tanks, but you got good options with them. They're not ductable. They're just upblast units, so they will receive a duct. I should say they did clarify that, but they just don't. The fans won't overcome much static pressure loss, so like 0.3 inches or less. All right, let's cruise to the next slide.
Yeah, and those are also good to -20 or so.
Let's see. I didn't have it in my notes. Yeah, off the top of my head, I believe it was down. It was in the negatives. I don't know if it was quite -20. I want to say it was like -10. But yeah, so it'll just compromise when you get down to those temperatures. A lot of times it'll either lower the high limit of your delivery temperature, or it'll just compromise the COP and kick on some other widgets to make it function.
But it would still work anywhere in Eastern Washington, obviously then.
Yeah, I think so. Okay, so we're switching gears now. We're no longer in the CO2 world. This is a product by Comac, the CXV, and it's R410A base. It's got pretty good heating capacity. It's 52 MBH, so about 3 or 4 times what a Sandon can do at 40 degrees outdoor air. And it makes 140 degree water down to 10 degrees Fahrenheit. So Seattle winter day of 24, this thing's cruising all the way through. And can still, by the way, it can still produce 120 down to -4. So it's a pretty robust unit for 410A product. They've got this cool feature where they use hot gas defrost as opposed to electric resistance. So what that does is cuts down the defrost time by about, I don't know, 2/3 or so. So like a defrost, electric resistance will kick on and take about 30 minutes to melt the ice. With that hot gas method, it's about 10 minutes, and then it's back up and running, making hot water again. They can do single pass or multi-pass. They can be configured either way, so you could use this for a recirc heater outdoors. That stackable frame option that you see in the picture, that's direct from the manufacturer. The that height, you know, you're still going to want to acoustically isolate that from your roof. It'll be some manner of separation, but pretty cool. They offer it so that you can stack them. This one's not ductable. There's no, it's just meant to blow outdoors. And these things are currently available and they're, I believe, installed. So there's no need to wait for them to come to the market.
Now, we will have things to talk about 410A refrigerant in a little while here, but
Yep.
do pay attention to that stacking concept, because if you got, you know, somebody that wants to have lots of amenities on the deck, then this could cut your space requirement in half.
Absolutely. All right, so here's the Comac CXV, and this one's based on R134A. And now these are designed to go in the garage. Like this, we're kind of making a switch from outdoor units to now garage units. These they want to be in environments that are 40 degrees or higher, and that's part of the R134A piece. That's a limitation of that refrigerant. But they've got a bunch of different sizes ranging from 138 up to 419 MBH at 70 degrees. So that, and the fans that come with them are pretty good. They're 1 to 2 inches of static, so they can shove some air through some ductwork and not miss a beat. This particular unit has the ability to produce up to 185 degree hot water. I would never need it for a plumbing system, I don't think, unless it was, you know, laundry or something. Or kitchen wash down maybe, but that's going to compromise your COP. So just be careful, like don't generate 185 just because you can. Only do it when you need it. And this, again, this unit is currently available. They're manufactured in Eastern Washington, I believe, in Colville. So anyway, that's about all I had to that one. Did you have a question, Duane?
Well, just wanted to add that if you're up against a storage capacity issue, remember it's BTUs that you're trying to store. So you could store your hot water at a very high temperature, and then it's running through a mixing valve anyway. But be aware that we have a requirement that if you do store at higher temperatures, you have to add more insulation on your tank.
Yeah, one thing I meant to mention earlier is your reference to the mixing valve, jog my memory, is that when these systems become more and more complex, I personally am more fond of digital mixing valves. So digital or electronic mixing valves have a tight delta T, meaning you send water in at 140, you can mix it or deliver it at like 142 or 145, so a tight delta T. The non-electronic valves typically want to see like a delta T of no less than 20, right? So if you send in 140, deliver 120, it can't really get any tighter than that. But also they're kind of self-diagnosing. They're self-diagnosing and self-modulating. Anyway, what my point is to get, with these systems becoming more complex and potential for things to go wrong, they're not that much extra money to purchase these, and it's much easier on your maintenance staff when things go sideways on you one day and you drop a heat exchanger or something and you need to go recalibrate your system. The digital TMVs are kind of there to support you. So anyway, all right, so Nile, same refrigerant, R134A, the C series. Very similar to the Comac in that it's ductable, got great fan static pressures that it can overcome. But one cool thing about this, Nile's looking into potentially switching out the refrigerant in these existing units. Say you purchase a C series and put it in and wanted to switch to R513A, they're looking into the ability to do that and not change out the equipment. So more to come there. That reach out to them. It was sort of mentioned to us in the presentation a couple weeks ago. But they're also working sidebar on an E series unit that is from the factory R513A. So it's outfitted entirely for R513A, which is going to give you different properties about how it functions. The C series operates down to 35. The E series would go down to like 10 or 15 degrees Fahrenheit. So pretty cool. And oh, by the way, we're not really getting into the C406.9 requirements much with a low global warming potential, but that R513A is something that would satisfy the 675 or less global warming potential to meet that credit. So start paying more attention to that global warming potential number if you're pursuing the C406 strategy for your building. Another cool thing is Nile's got their own multifamily sizing calculator on their website. So works just same outcome more or less as the eco sizer that we went over, but this one's more tabular. It's like Excel based, and you can play with the the different demands, high, low, medium. So that's available. Just go check it out on their website.
I'd be interested to know if anybody runs a calculation on both tools to see if they get you approximately the same result.
We did actually on that project that we were showing the sample floor plan of, and it was pretty close under the same assumption. So that's good news, right? It means both of them are right or both of them are wrong.
Right. And just note that Chris mentioned on this, you can potentially change out refrigerants in a few years on this. That's not typically possible currently for most situations. So it's a pretty good bonus.
Yep. Okay, so this one, before I switch gears to the next one, this one I wanted to bring up. There is the code section, exception number 2, that allows you to offset your air to water heat pumping needs with other technologies. So solar thermal, wastewater heat recovery, and other approved means. That's kind of leaving the door open for other opportunities. So I just want to remind everybody, it's not all air-based, right? There are other methods for you to tailor your hot water delivery systems with your building, and just gotta make good sense. So go jump to the next slide. So Piranhas are wastewater heat pumps. It's that diagram to the left. So on a normal operation, you're just taking all of your heated water, showers, laundry, whatever, and just literally draining it out the building, giving it away. What Piranhas do is they recapture that back into the water stream through the domestic water stream through a water-to-water heat pump. Now, I know it sounds a little gross, but there is a double wall heat exchanger in between you and that waste stream, so you can sleep a little bit easier. But think about it, like picture to right, a laundry, right? A commercial laundry with a Piranha in it, it's like a no-brainer. It's generating hot water, it's dumping it, but they're recapturing it, and I'm assuming that's helping their operations costs, right? So one thing to know is that Piranhas, they're limited up to about 80% of your domestic water demand. So they can't really get beyond that. So you will have to have another 20% or more of air to water heat pumps to get you the rest of the way. But still, I mean, it's an offset and something to think about. Let's jump to the next slide real quick. Yeah, so a sewage, consists of a sewage holding tank. You're routing all of your wastewater to it, and then your sidecar pumping that and making hot water to the side. One thing you want to be careful about is not locating this system below your sanitary connection in elevation, because what that would introduce is needing a lift station to then pump it back up to to your sanitary sewer connection. So you want to have gravity get you there, and then water-to-water heat pumps to gravity out, right? But again, this is all happening independent of outdoor air temperature. We keep talking about how cold is it outside. This system doesn't care how cold it is outside. And it's literally making hot water just after you use the hot water. So it's like this synergy flywheel effect. It's pretty cool to me. That I don't know, it's kind of a no-brainer. We haven't seen a ton of these projects yet. I don't know the exact reason why. I mean, cost-wise, it's not too much, out of the realm. I don't know. Maybe there's a little bit of, stigma associated with them. But anyway, I like to keep bringing them up because they're pretty nifty. So the moral of the story basically is just don't forget about other options, right? These are very much out there. They got good voltages, 208 3-phase, 460. I mean, it'll fit in most buildings. 108 up to 180 MBH per unit. You can pipe them in parallel. So anyway, that's my soapbox for wastewater.
And just to be clear, with any of these advanced technologies, new ideas, and like that, your friendly county public health department plumbing inspectors would love to have you come in and talk to them early and work out any issues and make sure everybody's comfortable with what's going on. Chris just mentioned that you'd want to locate one of these so that you didn't need to have a pumped sewage ejector to take you back up to a higher elevation. There's probably other issues like that. So they're interested in heading off problems before you're coming into the permit desk in a panic.
Right.
So,
yes.
That's us back again. Okay. You are allowed by the code to have a certain amount of supplementary electric resistance heat. That does not say supplementary gas heat, notice. And so, like we mentioned before, you can have it for temperature maintenance. You can have it for periodic defrost, heat trace on a pipe. You can, for low temperature air, if you're at a point where it's too cold for the compressor to get it with just compressor heat, and the temperature is below 40, and you can, as long as that compressor will keep providing heat to its ability, you can supplement with some electric resistance. And you can also have some electric resistance for individual water heaters. You know, you might have a high school that's got an art classroom way at the end of some wing, and you don't have, if it's not on that central system, then that's fine to be electric resistance. Refrigerant, I had to put that magazine cover on the corner there because that just came in my mail yesterday. But you can see that this is an issue that is on everybody's mind now in the profession. So we just had legislation that passed through in Washington State that's modeled after what's going on in California and elsewhere. And that says global warming potential of 750 would be your upper limit after January of 25. But that's not a permit date of January of 25. That's when the stuff is manufactured, which is probably just a few months before it's installed. So really, coming up very soon, you're going to have to be complying with these with these state regulations. So you've heard us talk about 410A and 134. Those are both, you know, each of those 2-3 times higher global warming potential than will be allowable. But that 513A fits in it nicely. And of course, CO2 with a global warming potential of 1 is great. It's actually more useful for water heatings at this moment because water heating typically needs a big lift from incoming cold temperature to outgoing hot. Whereas if you're just heating a space, so you have a hydronic system, that hydronic water is going to be coming back around just 15-20 degrees colder than it went out, and you know, geared towards making that kind of a small boost in temperature. So, but notice my diagram there that I pointed out that it's 50% leakage. That's it's about exactly 50% that appears to be of all refrigerants manufactured that lands in the atmosphere. The rest gets recovered or reclaimed, but half of it leaks out, and it's enormously destructive. So we're making progress, and the manufacturers are all hustling to get products out there that work.
Dwayne, a quick question. Do the state regs apply to domestic hot water or just AC that you're discussing?
They said to heat pumps. They said to air conditioners and to heat pumps. I'll have to go back and, that's a good question. I'll have to go back and look at that regulation, but I think it does. Do you know, Chris?
I don't. I was hoping you knew. Yeah, I'm not 100% sure. I will say, sounds like the way that I'm not abundantly sure familiar with 1050 yet, but it sounds like existing buildings, if you're in before that date, you can still keep your refrigerant at this point, right? You can
So
recharge them, you can work on them.
We have a definitive answer from Emma, who says it's just space heating. She just checked.
Thank you.
Interesting.
One thing I should say about the CO2 is that on the way into the Seattle code, we had a cost estimator working on this, and we had a big argument about whether moving from a traditional, say, gas-fired water heater to heat pump was going to add an extra $800 a unit to an apartment building or $1,800 to a unit building, and people were lined up on both sides of this. It turned out that those buildings that were using collections of those small stand-in units, maybe, you know, I saw one 50-unit apartment that used 4 of them. They were coming in at an extra $700–800 per apartment unit more than the traditional heating, whereas the R134A things that sit in the basement were coming in at more than double that additional cost. So it might be that the low global warming potential refrigerants are also your economical path for water heating. There's also federal law that's being worked on right now that's still, I think, not settled, and it looks like kind of like maybe we did with Freon a couple decades ago, that might be dealt with by simply raising the cost of replacement refrigerant each year until everybody replaces their things. So my prediction of the future, which is often not correct, but would be wise to go with the low global warming potential where you've got an option to do so. Okay, alarms. You just got to have something on there for when something is going wrong with the equipment, or you're not getting the proper water temperature coming out. Some alarm should ring, but my concern has always been, great, it's easy to spec and easy for somebody to do, but can you set up a system by which somebody who can do something about this will see the alarm and understand what it means? Chris, do you have an answer for me?
Yeah, I mean, you can have your BMS controls is not my strong suit, by the way, but you can have your BMS communicate to the appropriate personnel of an issue. You can send alerts and things like that. On projects that don't have BMS, like a lot of times mid-rise projects are not BMS projects, it'll be the controller itself that is the means of sending out that signal. Like Sandins, for instance, they have those controllers that we used on that project. Actually, they're not made by Sandin, but they push out data, and there's alarm contacts on it. So it's a matter of where are you going to alarm that? Is it going to go to a building maintenance office or an engineer's office, or is it going to be somehow wirelessly transmitted via email, text, something to the correct people? Because you're right, like if the building's crying for help and nobody hears it, that's no good, right? It's not going to help anybody. So my advice would be get familiar with the parameters of each of the devices, see if they have that capability, and if they don't, push for it. Otherwise, they're not going to meet this requirement.
And you probably want to you designers probably want to have a little chat with your owners to figure out what their preferences would be for who'd receive this alarm, and then I guess it would be the controls contractor that would hook all that together.
Right.
Probably be a good thing to check with commissioning later to make sure that that actually is all wired up.
That's right.
Okay, we'd be remiss if we were not going to discuss how all these rules apply to existing buildings, because in general, they will. But the ground rules for existing buildings are that in most cases, if you built it legally back in 1962, it can stay that way. You can repair it if it breaks. If it's anything to do with landmark protection, then we are very careful to make sure nothing we do is going to harm the historic value of the landmarks. But new stuff has to meet code. And those 3 bullet points are at the bottom are a special case. In Seattle only, we have what we call substantial alterations. I'm sure you all know and love this, where we're saying you've substantially extended the physical or economic life of the building with your project that's so big. We're treating that more or less like a new building. Same with a change of occupancy from a factory or warehouse, unheated to heated status. Those we do work on well. We do require that you either comply with the whole code, or more likely that you're permitted to do all the systems to code, but let your building envelope be a little less than code, or that you use energy modeling and you're allowed to have that building be a little worse than code. I just got to notice that I'm getting weak signals, so I'm going to turn off my camera here. So replacement. So a new system has to meet that whole requirement of the water heating section of the code, and there's an exception in there for if there's just one piece of equipment that's failing and it's an emergency. You gotta yes, we'll let you replace that like for like. But also earlier in the code, you needed to know that first rule I said that basically says any new stuff you put in has to meet code does apply here. So Chris.
Yeah, I mean, so that the exception is helpful, but I'm wondering in practicality how long that really can get you. Like, are you just going to keep doing that for the life of the building, or will 2 devices fail at once? At some point, there will be the need to switch over and modernize to comply with C404. And when that happens, it's, each building, there's no silver bullet solution here. I wish I could tell you that, like, hey, here's your answer, but it's not. Each building is a snowflake. When that happens, you just have to be prepared for some potentially very significant changes. I mean, you guys have listened to all this presentation to know that there's massive space impacts, cost impacts, potential electrical impacts to incorporating these systems for a building that was designed to be a gas boiler, right, or whatever else. I would say my advice would be to start thinking about a potential solution now and start engaging consultants to talk about it. There's some, I don't know if Duane, you could probably speak to this, maybe there's some manner of leeway or discussion or negotiation when, if you need 1,000 square feet of heat pump mechanical space and you have 200, there's no answer there. So what is the pathway? What is the game plan to get your building to keep moving for perpetuity? We think about it when you switch to heat pumps, you're probably talking about running into electrical service to the building potentially. If it was a very gas heavy building, you're talking about nixing outdoor amenity spaces or carving out parking of existing garages. Say your gas boiler plant was on the roof, but you had some parking space down low that you could deal with getting rid of. those mains, existing mains, are fed in the opposite direction of where they want to be fed with the new heat pump if it's located down in the garage. So, so that would involve demo, that would involve cost, that would involve probably potential shutdown, or at least some period of time, unless you ran the systems in parallel as you install them with the other system live. But anyway, it's sort of a bird's nest, and I can't tell you that it's easy. It's an easy cakewalk. It'll just, you should reach out to trusted advisors to help you get there, and also engage SDCI as well. That's all I got on it, Duane.
Yeah, we're aware that this is one of the many things that keeps my popularity ratings in the low single digits usually. But the thought here is that the city is, and to some extent the state now, is bound and determined to stop wasting or stop emitting carbon into the atmosphere. And some points along the way, like this one, are expensive. And the thought here is that yes, we know it's expensive and disruptive, and it's going to make your CEO angry, but there won't be any more economical point in the life of the building to do this than at that point where we needed to change out the water heating system anyway. And so, because then it's just the marginal cost, but it's much preferable to do that as part of long-term capital projects than to have it come in as, you know, some future mandate that might be at a less convenient time. Another thing to consider here, now we mentioned that, is the building performance standards. So any of you who have large buildings, 50,000 square feet and up, or work on those, then in the next few years, you're going to have to either meet an EUI target that has been set, or have a schedule of annual work you're going to do over a period of time that you can prove you make annual progress on. The reason I bring this into this forum is that those buildings you're looking at probably are not going to want to change their building envelopes. There's a lot of things they probably don't want to change, but water heating is probably going to be the easiest system to deal with for gaining extra efficiency, because it gets you that dual benefit of both reducing your carbon emissions and dramatically reducing your energy use. So I'm thinking that building owners looking over all their options are very much going to want to consider upgrading to heat pump water heating as a way of meeting their performance target. With that, our part of the presentation is done, and we're going to move over to our people from City Light.
So thank you very much, Duane and Chris. This is Sean. Folks, if you have any questions, this is now your opportunity to play Stump the Chump with Duane and Chris. Questions, questions, questions. In the meantime, Sarah and Colleen, if one of you could let me know who has your slides, I can make you the presenter. Thank you very much. Questions, questions, questions.
I do actually have slides already built into the rest of this, so you can just have, I can just advance here.
Okay. Questions before we, questions, 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 going once, going twice. I can say it's been a very informative talk. And Phoebe notes that Piranha, by the way, is being considered for a number of projects in Seattle, in case that's helpful for you guys. Okay, questions coming in. Who will inspect these systems? Mechanical, boiler, plumbing?
That come in from King County? No, we're discussing that right now, even as we speak, and you know, the county is typically in charge of inspecting everything touches potable water. But our boiler inspectors are do have jurisdictions over big tanks of hot water. They're the ones who make sure that it's properly seismically braced and connected. And so as far as the rest of how we deal with the heat pump water heating inspections, we are in discussions and haven't fully resolved it yet. But your first stop is the county, and then certain chunks of that they will send up to us to further check on. Remember that we also have to look at noise and perhaps structure to make sure that everything is accommodated, and so that might happen through our boiler inspectors, but we're still working on that.
Okay, one more. When will the city council decide when HPWH will be required for all commercial buildings?
That's been a slow process, and because this is Seattle and we do things carefully, so we don't know right now when it will be introduced into council, but I expect sometime this summer. And the effective date would still be January of next year if that goes forward.
Okay, thank you very much. That concludes the current questions. So with that, allow me to please introduce Colleen Butterfield and Sarah Braun from Energy Solutions.
Great, thank you. Could we go to the next slide, please? This might actually be.
Yeah, this is not Energy Solutions slides.
Oh, okay.
So Sarah or Colleen, do either of you have the slides? I can make you a presenter if you do.
We do, sure. I can take it.
Okay, Sarah, give me about 3 brief shakes of a lamb's tail, and I will make you the presenter. And Duane, I will need to come back to you for the end.
Okay.
Sarah, take it away. You have to go ahead and share your screen.
Great, and are you looking at a presentation or the webcam?
I am looking actually at a desktop, very lovely view of a mountain lake.
All right, let me take 1 second to pull this up. All right, how about now?
That's the one. Take it away.
Great, thank you. So hey everyone, we're really happy to be here. Colleen and I are implementers for Energy Solutions. We work closely with Emma to implement Seattle City Light's midstream HVAC program. So I'm the project manager for an HVAC and heat pump water heating program. And Colleen, I'll let you introduce yourself as well.
Double muted myself. Hey everyone, Colleen Butterfield with Energy Solutions as well, part of our trade ally management team and based out of Portland, Oregon.
Great. So today we just wanted to cover some information about this midstream HVAC and heat pump water heating program that Seattle City Light offers. The program overall is actually administered by Seattle City Light and Puget Sound Energy in the territory shown in the map at the right. And as the program implementer, we at Energy Solutions provide support and guidance for distributor and contractors who are participating in the program. So really the high level idea is that contractor incentives for selected energy efficient equipment are available through enrolled distributors. Contractors are encouraged to pass these incentives through to the end use customers, but it's not required. So after receiving an incentive from an enrolled distributor, for a qualifying heat pump water heater, ECM circulator pump, or heat pump under 5.4 tons. You can use that incentive as you see fit to support future high efficiency sales and really just make energy efficient equipment available to Seattle City Light customers. Really everything qualifies for this program. For heat pump water heaters in particular and ECM circulator pumps, we cover residential and commercial installations. We cover replacement and new construction installations. And the boundaries around qualifying equipment are really tied more to efficiency and energy savings, which Colleen will cover a little bit later. The program goals overall are to promote the stocking and upselling of high efficiency equipment, and then by doing so to reduce energy use and carbon emissions through optimal HVAC and water heating system design. So with that, we'll move on to how you can participate in this program. Really, this is designed to be as simple as possible for you. The idea is we have a set of participating distributors, and all you have to do is identify which distributors are participating in this program using lists available on Seattle City Light's website. Once you know that your distributor is participating, you can purchase equipment for qualifying installation through that distributor, and then just share a select subset of customer information. We try and keep this as simple as possible again. So really all your distributor needs from you is the installation address and some simple information about the project, whether that's the building type or the project type or the installation date. Once this has been provided, the distributor will provide you with a rebate and you're done. You don't need to apply for rebates directly. You can lean on the distributor to complete all of the application information, apply for the rebate. And we'll show a little more about how this works on following slides. So who are our participating distributors? If you need to access a rebate for qualifying high efficiency equipment, you can reach out to any of the distributors shown on this slide. We have a solid group of water heating distributors as well as some HVAC distributors for those of you who also work with heat pumps. And all these distributors are engaged in the program. Some of them consider it one of the most successful rebate programs that Puget Sound Energy and City Light have run. And they're fully on board to help you access some qualifying energy efficient heat pump water heaters and receive the associated incentives for that equipment. As far as the program process goes, I do want to show a little more detail on how you might see the program play out. Really, the process starts when you have a qualifying installation. A customer might reach out, and when you purchase qualifying equipment for a project from a distributor, they'll provide the rebate to you directly. Once you receive it, you can offer a discount to the customer, or you can reinvest that rebate in trainings or administrative costs, however you see fit. Really, all you have to do at that point is decide how to use the rebate and install the equipment. And again, we encourage pass-through of the rebate to the customer, but it's not required. You can see in these bottom 3 lines on this slide that once you've received the rebate and are moving forward with the installation, everything else is taken care of behind the scenes. So a distributor will submit an application to Energy Solutions. We'll work with Seattle City Light to reimburse the distributor for the incentive that they provided. But this is all kind of behind the scenes for you and hopefully off your plate. And with that, I'll turn it over to Colleen to talk specifically about some of the eligible installations for the program.
Awesome, thanks, Sarah. So since we've been focusing on heat pump water heaters on this call, I'll talk specifically to that here. There is a $500 rebate per heat pump water heater unit that goes to the contractor and ideally on to the homeowner or the business owner. And there is a 1 per residence limit on heat pump water heaters for Seattle City Light and 2 per residence for Puget Sound Energy. The distributors that are enrolled in this program represent all of the major heat pump water heater manufacturers. But if you happen to find, a distributor that you're working with that's not participating with us yet or doesn't stock a model you're looking for, please have them reach out to us and we'll definitely get them signed up so you can get your rebates. Next slide, please, Sarah. Here we just wanted to give you an idea of what the eligibility looks like as far as the efficiency levels and what some of the different incentives are. So we break down the equipment by size and energy efficiency, and we utilize the AHRI test standards for both HVAC and heat pump water heaters. The heat pump water heaters, as we mentioned, are $500 per unit across the board. So as long as they meet the minimum 3.0 COP and are at least 200 gallon storage or below, they will be eligible. So this information is all available via the Seattle City Light and PSE websites as under the residential rebates, but you're also welcome to reach out to us to get everything in a nice table format here too. We have a PDF we can share with you. So at the end, we'll have a contact slide, so you have our contact information as well.
Pardon the interruption, may I ask a quick question? My organization self-performs a lot of our equipment installation, purchasing from some of these distributors. So even though we are not a contractor, can we get these incentives?
Yes, you would be acting basically the same as a contractor in this setting. So you would still provide the distributor that you're purchasing the equipment from the same information that is required, which we can go over. If you want to reach out to us, we can talk about that in more detail, but you would essentially be acting as a contractor for purposes of the program. All right, let us know if there's any other clarifying info you need, but we'll move on to the next slide here. So while we've been talking about heat pump water heaters, we also wanted to point out that there are, of course, high efficiency models and all sorts of other types of equipment. And we've all been working hard with the distributors in the region to ensure that there are high efficiency options in stock across the board, including things like VRF and water source heat pumps. So we really encourage you to work with your distributor on competitive pricing for any heating and cooling equipment, whether it's space or water. And we also have some new incentives coming out that for FEI rated fans and PEI rated pumps. So yeah, lots of good high efficiency equipment out there in the marketplace right now. We can move on to the last slide. And this is our contact information. The top left there is a hotline number and a group email address for those of us here at Energy Solutions. We're always happy to hear from you, and we can send you all sorts of resources, including territory maps, zip code lists, incentive sheets with the full list of equipment eligibility requirements, and the full list of participating distributors. So don't be shy, feel free to give us a call if you have additional questions. And of course, there's also additional info on the websites of our participating utilities. And yeah, we hope to hear from you. Thanks for having us.
Colleen, just to clarify, when heat pump water heaters are required for multifamily starting next January, then this would no longer be available, right?
So Emma, feel free to jump in if you'd like, but we are working through ways to continue promoting and incentivizing the sales of high efficiency equipment. It might look a little different next year, but the intent would be to incentivize heat pump water heaters at this level through the end of 2021 at a minimum, and then to continue promoting sales after that. And Emma, feel free to add if you have anything.
Yeah, thanks, Sarah. We are not quite there to announce what's going to happen in 2022, but likely scenarios are just simply reducing the savings claimed for new construction projects, understanding that code is pushing efficiency.
Excellent.
Thanks. We do have another question. So do these midstream rebates apply to central heat pump water heat systems such as one finds in MF buildings? I'm not sure what MF building is referring to. Multifamily, of course.
Yeah, actually, Duane, can you share your slides again? And that's a great question, as it transitions us to what is still offered by Seattle City Light.
You'll just make me the presenter again, Sean?
Working on it. Give me just a second.
Should be all set.
Ah, great, great.
Are you good now?
Yes, I can see the slide deck. Excellent. So I'm here with my colleague, Julie Banerjee. I'm the retrofit program manager for Seattle City Light programs, and Julie is the new construction program manager for multifamily and commercial and industrial. Sorry, go back to there you go. So here's a list of all of the heat pump water heater incentives that we offer still through Seattle City Light. There's a variety of different building types and vintages where we try to encourage the heat pump water heating. So if you're a single family do-it-yourselfer, you go to Home Depot, Lowe's, online, you would purchase a qualifying, standard heat pump water heater tank like A.O. Smith, Bradford White. You go to our website, submit an application, we mail you a check for $500. If it's contractor installed at single family, low rise, or multifamily new construction, that's where the midstream rebate would come in. Typically, we're looking at same type of equipment you'd see at a retail store. Typically, they're less than 90 gallons, but we do allow up to 200. And those are also $500 from the distributor to the contractor. And then Seattle City Light, we offer custom or semi-custom incentives for the single and multi-pass centralized systems. So those are an application. Go to our website, create just a generic, hey, I'm interested in pursuing incentives with Seattle City Light. We would assign you an energy management analyst to help work through your project and calculate the savings. And we offer 24 cents per kilowatt hour for retrofit. And I'll pass it on to Julie to talk about new construction.
Great. And then in new construction, what we're looking at are the incentive rates for projects permitted under the 2015 Seattle Energy Code. And we have three options for multifamily new construction that for centralized systems based on the technology, the heat pump COP, a standard or a high, and that can either be $200 per living unit or $350 per living unit. And then with the addition of a CO2 working fluid, you can get up to $500 per living unit. Similarly, in commercial new construction, we support single or multi-pass centralized systems at 27 cents per kilowatt hour. Again, we were talking a little bit about how this will change both with the 2018 Energy Code and in January of next year. And we have updates coming pretty soon about those.
And I just wanted to clarify one thing, that if you're like a small commercial kitchen and you bought a commercially applicable unit through a midstream program, that's still something that we would incentivize through midstream. And there's no limit on the quantity there for small commercial purchases.
I'm kind of interested in the multifamily new construction for a central CO2 system, that second row from the bottom. You're getting $500 a living unit, and we've been hearing that it's maybe the total increase in cost over conventional is $800 per living. So you're really almost covering the cost of the additional cost of having a CO2 heat pump.
Yes, depending on who you talk to, but yeah, the intent is to cover a large amount of the incremental cost until it becomes a requirement. So we're hoping people really leverage these incentives this year.
Yeah. Sean, are there questions coming in on this?
I am not seeing any yet, but anybody else going once, going twice? This is your opportunity to query these excellent building professionals. Learn from them. I am not seeing any other questions come through at the moment.
All right. We'll keep everybody here though. Just a word to everybody who's interested in this topic that a proposal that's similar to what's in the Seattle Code there that we've been talking about is now before the state technical advisory group for the, to have that become statewide code. And I'm sure there are those of you who are on either side of this issue, but July 9th, 10 o'clock in the morning, we'll be discussing this, and those links are there. It's also pretty easy to find on the State Building Code Council website.
Okay, before we go to the final slide, there is one other question that a late breaking question. Why have a kicker for CO2 versus other low GWP? Emma or Julie?
Yeah, I can talk to that. When this was established, that was one of the first technologies emerging in the market that was proven. But like I mentioned, we're reassessing how we support hot water heat pumps, both because of code changes and the requirements around working fluid. So this was set a couple years ago, and we're looking at it now and how it might work moving forward.
Okay, terrific, thanks. I was muted, of course. I do not see any other questions coming in, so Duane, why don't you take us to the outro slide, please? So on behalf of the Lighting Design Lab, which once again is powered by Seattle City Light and is a service brought to you by Seattle City Light, I'd like to thank you all for coming and participating in the third of 3 seminars that we had regarding heat pump technology. The upcoming course series that will be next is still under some discussion. So stay tuned, please, to the Lighting Design Lab webpage for the next educational opportunities that we'll be bringing to you. If you want to contact Duane, of course, Duane's information is Duane Jonlin at seattle.gov. My compatriot Armando Berdil is Armando Berdil at seattle.gov. Or you can reach me at Shaun Darragh, SHAUN.DARRAGH at seattle.gov, somewhat unsurprisingly. Or email us at lightingdesignlab@seattle.gov if we can be of any assistance. In the meantime, once again, handouts and a recording of this broadcast will be posted to the Lighting Design Lab webpage within a few days under our educational tab. In the meantime, thank you very much to all of our panelists, Duane Jonlin, Chris Little, Sarah Braun, Colleen Butterfield, Emma Johnson, and Julie Banerjee. And with that, I will say, have yourselves a lovely afternoon. Please take the online survey when you exit the webinar. It's very helpful for us. And we will see you next time. Thanks, everybody.
Bye.